Hi again everyone, welcome back to College Algebra, and today we're in section R.6, and today we're looking at rational exponents. So you may remember that in section R.3 we reviewed some of our exponent rules, the product rule and the three power rules, and we also talked about the zero exponent rule. And today we're picking up the rest of our exponent rules, so we're going to be looking at negative exponents and the quotient rule for exponents, and then we'll look at rational exponents, which just means exponents that are fractions. So let's get started. Now first, here is the negative exponent rule. You probably have seen this before, but we just need to be reminded. Let n be an integer, and let a be a non-zero real number. So n is a positive or negative whole number, and a is any number except 0. If you have a to the negative n power, you can restate that as 1 over a to the positive n power. So you can think of this as a negative exponent means we move the base to the denominator. That's one way to think of it. So let's practice here restating each expression without negative exponents, and then we will evaluate if we can. And notice that it says assume all variables represent non-zero real numbers. So in other words, we just don't have to worry about what would happen to a fraction if one of our variables is 0. Okay, we'll start here in part A with 4 to the negative 2. Now remember, the negative exponent rule says we can make this exponent positive if we move this whole thing to the denominator. So I'm going to say that this is equal to 1 over 4 to the positive 2. So we know 4 to the second power is 16. So this is going to end up being 1 over 16. And since that cannot be simplified, we are finished with that part. Now let's look at part B. Here we have negative 4 to the negative 2. Now you'll remember from when we talked about our zero exponent rule that an exponent does not apply to a negative that's sitting in front of the base unless that exponent is applying to everything inside a pair of parentheses. But we don't have any parentheses here. So this negative 2 exponent is only applying to the 4 and not to the negative. So when I restate this with a positive exponent, I'm going to leave the negative in the top of the fraction. And I'm just going to move 4 to the negative 2 to the bottom where it becomes 4 to the positive 2. So again, this negative stayed in the top because this exponent is not affecting the negative. So I just left it there. And now again, 4 squared is 16. So we have now negative 1 over 16. Now moving on to part C, here we have in parentheses x times y, and it's all raised to the negative third. So this negative 3 exponent is going to apply to everything inside the parentheses, and we'll just move the whole thing down to the denominator. So now it's 1 over x times y all to the positive third. And we will need to work this out so that we no longer have parentheses. So we'll apply this third power to both factors inside the parentheses, and that's going to give us 1 over x to the third times y to the third. And since no further simplifying is possible and all exponents are positive, this one is in final form. Now look at part D. Here we have x times y to the negative third, and there are no parentheses. So in this case, the negative 3 exponent is applying only to the y. So the x is going to stay in the top, and the y to the negative third is going to move to the denominator so it can become y to the positive third. So we're going to have x over y to the positive third. And now, since no further simplifying is possible, and since all of our exponents are positive, this is in final form. Now I want to point out to you something that's a very common mistake among new algebra students, and that is that a negative exponent indicates a reciprocal, not a sign change of the expression. So a lot of times students think that 3 to the negative 2 is going to mean negative 9, but that's not the case at all. The negative exponent does not give us a sign change in the answer. You know now that 3 to the negative 2 is going to be 1 over 3 to the positive 2, which is 1 over 9. So a negative exponent indicates a reciprocal, not a sign change. Now, because a negative exponent indicates a reciprocal, we can write the negative exponent rule this way instead of the way I showed you before. If we have a fraction, a over b, and it's raised to a negative power, we can make that power positive by simply doing a reciprocal on the base. So a over b to the negative m is going to be equal to b over a to the positive m. So you see we kind of used up the negative exponent, so to speak, by flipping the fraction over. So that's how the reciprocal is accomplished. So if you have a fraction that's raised to a negative power, a lot of times this is an easier way to apply the negative exponent rule instead of moving the whole fraction to the denominator, because then you have what's called a complex fraction, and these are harder to work with. You don't want a fraction that contains a fraction. So we use this form of the negative exponent rule to avoid that situation. So let's practice with that. The instructions here say write each expression without negative exponents and evaluate if possible. And our first expression is 2/5 to the negative third power. So we just learned on the last slide that we can restate this with a positive exponent if we just do a reciprocal on the base. So this is going to be 5/2 to the positive third power. And now we can use our power rule number 3, and we can apply this outside exponent to both the top and the bottom. So that's going to give us 5 to the third over 2 to the third. And we know 5 to the third is 5 times 5 times 5. That's going to be 125. And we know 2 to the third is 2 times 2 times 2, so that's going to be 8. And that one is simplified. And now let's do the same thing for part B. Here we have 3/4 to the negative 2 power. So we can write this with a positive exponent by saying 4/3 to the positive 2 power. And then we can use our power rule number 3 to apply this outside exponent to both top and bottom. So that's going to give us 4 squared over 3 squared, which is 16 over 9, and that cannot be reduced. Now, before we go on to the next slide, I do want to point out to you that both of these are improper fractions, and they could both be converted to mixed number form. But in algebra, we never ever really want to go to mixed number form. It's much more acceptable to leave any improper fractions in improper form. So don't get the idea of simplifying confused with the idea of converting to mixed number form. These are improper fractions, but they are simplified because the top and the bottom cannot both be divided by the same thing, so we'll leave these in this improper form. Now let's talk about the quotient rule for exponents. So suppose you have m and n that are exponents and they're integers, and let a be a non-zero real number. So we just won't have 0 as a base. But if you have a to the m power divided by a to the n power, you can simplify that by saying that's going to be a to the m minus n power. And here are some examples for us to practice with the quotient rule. So we'll start off with 12 to the 5th divided by 12 to the 2nd. Well, we see here that the bases are the same, so that means we can subtract the exponents. And 5 minus 2 is going to be 3. So 12 to the 5th divided by 12 to the 2nd is going to be 12 to the 3rd. Now that is how the rule works, but I also want to show you why it works. So just real quickly, let's remember that 12 to the 5th means 12 times 12 times 12 times 12 times 12, so 5 of them. And 12 to the 2nd, of course, would be 12 times 12. Now you know that any number divided by itself is 1. So what we can do here is divide out this pair of 12s, and we also can divide out this pair of 12s, and you see what's left over is 12 to the 3rd. So that's why we can just end up subtracting the exponents. And notice that wherever you have the larger amount of 12s, that's where the leftover 12s are going to be. So I have 5 12s in the top and only 2 in the denominator, and so the leftover 12s ended up in the top. And that's how you always can know that you're using the quotient rule correctly. Now let's look at part B. Here we have a to the 5th over a to the negative 8th. Now just applying our quotient rule, we could actually say that this is going to be a to the 5 minus negative 8. Remember, that's how the quotient rule works. It's the top exponent minus the bottom exponent. So 5 minus negative 8. And of course, minus negative is plus, and so this would end up being a to the 13th. But here's an alternate way to look at this problem, and I think a better way. Instead of working with these exponents while one of them is negative, let's use our negative exponent to write it with positive exponents first. You know that we would bring this a to the negative 8 up to the numerator, and then we would have a to the 5th times a to the 8th. And of course 5 plus 8 is 13, so we would get a to the 13th. And if you have a good handle on the negative exponent rule, I think this is actually a more foolproof way of handling a problem like this. Now let's look at part C. Here we have 16m to the negative 9 all over 12m to the 11. So I'm going to do what I told you to do on the last part of this example, which is I'm going to make all the exponents positive before I start trying to add and subtract exponents. So notice that the 16 and the 12 don't show any exponents, so we know that they are to the first power. So in effect, they already have a positive exponent, it's just not written. So I'm going to leave the 16 in the top. The m to the negative 9 I can have a positive exponent if I put it in the denominator. So I've done that. And then 12 already has a positive exponent, so leave it in the denominator. And m to the 11th already has a positive exponent, so leave it in the denominator as well. And now we can do a little simplifying. Let's work with the coefficients first. So I see that we have 16 in the top and 12 in the bottom, and I know that both of these numbers can be divided by 4. So I'm going to mark those out. 16 divided by 4 is going to be 4, and 12 divided by 4 is going to be 3. And now let's see where we are. We've got 4 in the top, and in the bottom we've got a coefficient of 3. I'm going to go ahead and put that first. And then the rest of the factors in the bottom are m to the 9th times m to the 11th. And of course, when we're multiplying variables like this, if the bases are the same, we add the exponents. That's the product rule. So that's going to give us m to the 20th. And now, because this is fully simplified and the exponent is positive, we're finished with this one. And let's look at part D. Here we have 25 r to the 7th, z to the 5th, all over 10 r to the 9th, z. I'm going to go ahead and just recopy it so it's larger so I can write on it. And now let's see what we can do with these coefficients. 25 and 10 can both be divided by 5, so let's do that first. 25 divided by 5 is going to give us 5, and 10 divided by 5 is going to give us 2. And for the rest of this, we'll be applying the quotient rule. So I'm going to go ahead and get to our final answer. We have 5 in the top, 2 in the bottom, and now let's look at the r's. Notice that we have 9 r factors in the bottom, and we have 7 r factors in the top. Now 7 minus 9 would be negative 2, but then we would have to apply the negative exponent rule. What I want you to do is always start your subtraction with the larger exponent. 9 minus 7 is 2, and we know the leftover r's are going to be in the bottom because of what I showed you back here. If you had 9 r's all lined up in the bottom and 7 r's all lined up in the top, and you canceled, you would see the leftover r's are in the bottom, and how many leftover r's would there be? Well, 9 minus 7 is 2, so we're going to have r squared in the bottom. Now for z to the 5th over z, let's remember that this z is z to the first power. Even though no exponent is written, it has to be to the first power because we see the z there. So 5 minus 1 is going to be 4, and there are obviously more z's in the top than there are in the bottom. So we're going to have here z to the 4th in the top. And here all of our exponents are positive. Everything is fully simplified, so this one is finished. Here's another example for us to just continue practicing with the negative exponent rule. It says simplify each expression, write answers without negative exponents. So let's take a look at part A. Here we have 3x to the negative 2 times 4 to the negative 1, x to the negative 5, all squared. And you have to decide how you're going to approach the problem. One thing you could do might be to apply this outside exponent of 2 to what's inside the parentheses first. I actually prefer to restate the problem with all positive exponents before I do anything else, and you know that from the last example that we did together. And the reason I want to do that is because I'm afraid if we don't, some of us are going to want to multiply 3 times 4. But this 4 is not available for multiplying times 3 because this 4 has an exponent. So remember from order of operations that exponents have to be dealt with first before we do any multiplying. So in order to just prevent careless mistakes, I'm going to go ahead and eliminate all of the negative exponents right off the bat. So right here with this 3x to the negative 2, we know the negative 2 exponent applies only to the x. So I'm going to write this as 3 over x to the second power. Now, within these parentheses, both of these factors have negative exponents. So I'm going to keep the parentheses and the square exponent out here, but I'm going to move both the 4 and the x into the denominator. So it's going to be 4 to the first power in the denominator and x to the fifth power in the denominator. Now you can't leave the top of a fraction empty, so we'll need a 1 there. You know, when 1 is a denominator, we don't have to write the 1, but when 1 is a numerator, we do have to write that because, again, you can't leave the numerator of a fraction just empty. All right, now let's go ahead and apply the outside exponent, this 2. So we'll be squaring everything inside the parentheses. So I'm still going to have my 3 over x squared outside, and then I'm going to apply this 2. So I'm going to have 1 squared, and in the denominator I'm going to have 4 squared times x to the fifth squared. So you see we just applied that 2 to everything inside. And now let's simplify that. I still have 3 over x squared, but now 1 squared becomes 1, 4 squared becomes 16, and x to the fifth squared becomes x to the 10th, because you can see this is a place where we would apply the power rule, so we would be multiplying these exponents. And now finally I'm ready to deal with the multiplication. So I see that 3 times 1 is going to be 3, and in the denominator we have x squared times 16 times x to the 10th. So of course the coefficient there in the denominator is going to be 16, and then x squared times x to the 10th is going to be x to the 12th. And 3 over 16 cannot be simplified, and the variable has a positive exponent, and so this one is in its finished simplified form. Now let's look at part B together. So here we have 12p to the third q to the negative 1 all over 8p to the negative 2 times q. And again, I would prefer to have all the exponents positive before I start trying to add and subtract exponents. So what I'm going to do is recopy the problem, and any factor that has a negative exponent I'll move to the other end of the fraction. So this q to the negative 1 is going to have to go to the denominator, and this p to the negative 2 is going to have to go to the top. So we'll just go one factor at a time. First we have 12, that has a positive exponent, it does not need to move, it stays in the top. Then we have p to the third, that also stays in the top. This q to the negative 1 needs to move to the denominator, so I'll go ahead and put that there. In the denominator, this 8 does not have an exponent showing, that means its exponent is 1, so it stays where it is. We only move it if it's negative. P to the negative 2 has a negative exponent, move that to the top. And then this q has no exponent showing, so its exponent is positive 1, so leave it where it is. And now what I'm going to do is just regroup and see where we are. So in the top we have 12p to the third times p to the second. We know that's a total of 5p factors, so that's going to be 12p to the fifth. 3 plus 2 is 5. And in the denominator we have q times 8 times q, so of course that's 8q squared. And now you can see we have all the p's gathered up here and all the q's gathered up here. And so the variables are as simplified as we can get them, and all that's left to do is simplify the coefficients. So both of these coefficients can be divided by 4, and we'll go ahead and do that. And we'll say 12 divided by 4 would be 3, and 8 divided by 4 would be 2. So our final result is 3p to the fifth over 2q squared. Now let's look at part C together. And this one is a little more complicated than the two that we just did. So here we have 3x squared all to the negative 1 times 3x to the fifth all to the negative 2 over 3 to the negative 1 x to the negative 2 all raised to the second power. Now there are a couple of different ways you could treat this. You could move these parentheses down to the denominator so that these exponents would become positive. And of course, in the denominator, this exponent already is positive, so this parentheses would not move. You could do that. I decided not to do that. I decided to go ahead and apply these outside exponents to the parentheses that they are acting on first. And then I'm going to move all the negative exponents to get everything positive. So let's go ahead and do that. So right here I have 3x squared all to the negative 1. So that's going to make 3 to the negative 1 times x squared to the negative 1. And then I have 3x to the 5th all to the negative 2. So that's going to make 3 to the negative 2 times x to the 5th to the negative 2. In the denominator, we'll apply this outside 2 to the parentheses. So we'll have 3 to the negative 1 all to the 2nd times x to the negative 2 all to the 2nd. All right, now I'm going to go ahead and do these power to power parentheses. So that's going to give us 3 to the negative 1 times x to the negative 2, because you see 2 times negative 1 is negative 2, times 3 to the negative 2 times x to the negative 10. And that's all over 3 to the negative 2 times x to the negative 4, because negative 2 times 2 is negative 4. All right, now you can see all the exponents are negative. Everything's going to have to move. So when I recopy this, I'm going to move these bottom factors to the top and each of these top factors to the bottom, because each one of them has a negative exponent. So that's going to give me in the denominator a 3 times x squared times 3 squared times x to the 10th, and in the top 3 squared times x to the 4th. Now one thing that I notice is that I have 3 squared in both top and bottom. Of course 3 squared is 9, but either way you have the same factor in the top and in the bottom. So we can go ahead and cross those out. And let's see where we are then. That gives us x to the 4th over 3x to the 12th, because x squared times x to the 10th is x to the 12th. And now notice that we have x's in both top and bottom. Where do we have the most x's? Well, we have 12 of them in the denominator, and we only have 4 in the top. So the 4 in the top are going to cancel out 4 of the bottom ones, and 12 minus 4 is 8. So we're going to have 8x factors in the denominator. So if I cancel out all 4 of the x's from the top, can I leave the top empty? You know from previous discussions the answer is no, we cannot leave the top empty, so there'll be a 1 in the top. So finally I'm going to have 1 over 3x to the 8th. And this is fully simplified and the exponent is positive, so we know that's finished.